Section 8.1, Exploring Exponential Models. An exponential function is a function with a general form of y equals a, b, x, where x is a real number. A is not allowed to be 0. If it is equal to 0, I would have a function of y equal to 0. Therefore, that would be a function that intersects the origin at 0 and would be a graph of a horizontal line. B must be greater than 0, and b cannot be equal to 1. If b was equal to 1, again, my function would be a horizontal line that would intersect at the value of a. An exponential function with b greater than 0 is called a growth model. When b is greater than 0, then b is the growth factor. An exponential function with b that is less than 1 but greater than 0, in other words, a fraction between 0 and 1, then it is a exponential decay. An asymptote is a line that the graph approaches as either x or y increases in absolute value. In other words, our graph of our exponential function, whether it is a growth or decay, will approach a horizontal line, in this instance a horizontal line, that it will get very, very close to that horizontal line, but will not touch or intersect that line. And that line is called the asymptote. Let's take a look at my first example. Here I have y equals 2 to the x. Here my base is 2. That is a value of b that is greater than 1. Therefore, this is a growth factor. And my x is my real number. Let's start substituting in and calculating some y values. Let's have x equal to negative 3. That gives me 2 to the negative 3. Since I have a negative exponent, I know my base needs to drop to the denominator. So 2 will go to the bottom. And if I have nothing on top, that becomes a 1. So that's 1/2 to the third, which is 1/8. 2 to the negative 2 gives me 1/2 to the second power. Again, a negative exponent drops that base down, and that gives me 1/4. 2 to the negative 1, that puts the base down, which is going to give me 1/2. 2 to the 0, anything to the 0 power is 1. 2 to the first is 2. 2 squared is 4, and 2 cubed is 8. Now let's plot those points. I have a negative 3 to the 8th. I have a negative 2 and 1/4. It's going to look very similar since they're very close. Negative 1 plots at a half. 0, 1, 1, 2, 2, 4, and 3, 8. And you can see, if I connect my points, from left to right, my graph increases, or as we've stated already, my value of b is greater than 1, a growth factor. We can also see that as my line approaches my x-axis, or at y equals 0, I have a line that my graph will come very, very close to, but will not intersect. As a matter of fact, I will not have any y values that are negative. As I decrease my x values, my value for y gets extremely small, but will not intersect my x-axis, and also will not cross over to go negative. Therefore, that creates a horizontal line that will not be intersected by my graph. In other words, an asymptote. Also, I can determine my domain and range. My domain, or my x values, can be any real number on my x. So x equals all real numbers. But my range, as you can see, or my y values, can be any value of y that is greater than 0. Not equal to, because my function will get very, very close to this value of y equals 0, but will never, ever intersect it. So this is my domain and range, and I have my asymptote. On my next example, I have y equals 3 to the 2x. 3 is my value for b. b is greater than 1, therefore this is a growth function. And my 3 is my growth factor. And I have an exponent of 2 to the x. Here, when I substitute in a negative 3, I get 3 to the negative 6, which equals 1/3 to the 6th. And when I substitute that into my calculator, I get 0.001. Substituting negative 2, I get 3 to the negative 4, which is 1/3 to the 4th power. When I use my calculator, I'm going to get 0.012. Negative 1, when I substitute, I get 3 to the negative 2. That's going to give me 1/3 to the 2nd power, which is going to be 1/9. 0, anything to the 0 power, is 1. 1 is going to give me 3 squared, which is 9. 2, when I substitute in 2, I get 3 to the 4th power, and 3 to the 4th power is going to give me 81. And when I substitute in 3, I get 3 to the 6th power, and 3 to the 6th power is 729. So you can see exponential functions grow extremely fast. So let's plot our points. I'm going to have negative 3.001, extremely close, but will not intersect the x-axis or y equals 0. I have a next point, which is a negative 2.012. My next point, negative 1, is 1/9. 0.1. 1/9. And from there, my points plot extremely high. So if I plot these, I'm going to have a rapidly increasing graph, which represents, as we stated here, that b is 3. It's greater than 1, therefore it's a growth function. I also can identify my asymptote with my dashed line. In other words, the line that the function will get extremely close to, but will not intersect, and that is at y equals 0. It's not always at y equals 0, but in the last two cases it is. I can find the domain again. X can be, as you can see, all real numbers. And again, in this situation, my range, or y values, is y is greater than 0, not equal to, because my graph will not intersect my horizontal line, or x-axis, at y equals 0. Again, range, domain, and asymptote. In this example, I have function s of t equals 2 to the 1/4 t. My b value on this exponential function is 1/4. That value is between 0 and 1. Therefore, I know this exponential function is a decay. When I work this problem out, I want to take 1/4 to the t power. Work that solution out, then multiply that by 2 to find the value of s of t. When I substitute in my values for t, I'm going to get a negative 3, 1/4 to the negative 3 power. That means I have 2 times 1/4 to the negative 3, which is really 2 times 4 to the 3rd, because that negative tells me I'm going to find the reciprocal of 1/4, which gives me 4, and then I take the cube of that. So 4 cubed is 64, times 2 is 128. Similarly, I'm going to have 2 to the 4th squared, which is 32. Negative 1, when I substitute in, I get 2 times 4, which is 8. Anything to the 0 power is 1. 2 times 1 is 2. When I use 1, that's 1/4 to the 1st power. 2 times a 4th is a half. 2 is going to be 1/4 squared, which is 1/16, times 2 is an 8th. And cubed is going to give me 1/64, times 2 is 1/32. Now, I can plot those points. Negative 3, 128 is too big for my coordinate plane, and so is negative 232. But I can plot a negative 1, 8. And I continue with 0, 2, 1, a half, 2 1/8, and 3 1/32. Now I can connect my points. And as you can see in my graph, from left to right, I am decreasing. That's how I know that this is a decay. Also, by viewing the value of b between 0 and 1, I can find my domain, my x values, and that can be all real numbers. And my range in this situation is going to be y is greater than 0. That tells me that my asymptote is going to be at y equal to 0. Therefore, my function will decrease to a point that it gets very, very close to my x-axis, but will not intersect my x-axis, which is y equals 0. My next example, I have y equals 0.2 to the x. Again, my b value is between 0 and 1, therefore this is going to be an exponential function that is a decay. When I substitute in, I'm going to have a -3 as my exponent, 0.2 to the -3. The negative tells me I need to find the reciprocal, which is 1 over 0.2, or I know 0.2 as a fraction is 1/5. 1 over 0.2 or 1/5, when I find the reciprocal because my exponent is negative, is going to give me 5. 5 cubed is 125. -2 is going to be 5 squared after the reciprocal because it's a negative exponent, is 25. -1 is 5. 0 is 1. 1 is 0.2. 0.2 squared is 0.04. And 0.2 cubed is 0.08. -1 at 5. 0 at 1. 1 at 0.2. 2 at 0.04. And 3 is 0.08. I can then connect my points. Then I can find my domain, which x will be all real numbers again. My range, which is y is greater than 0, which also tells me my asymptote is going to be, again, at y equals 0. Therefore, my decay function will not intersect or even touch my x-axis, which is y equals 0. In this example, I want to write an exponential function in the form of y equals a b to the x for a graph that includes the given points. Here I have 2, 45, and 3, 135. I've written the steps for the procedure to actually write this as y equals a b to the x. So let's begin. Our first thing to do is to use the first point, which is 245, and solve for a using my exponential function. Here I have y, which is 45, equals a, which I don't know, I'm solving for that. B, I don't know, I can solve for that in a little bit. And my x, which is 2. So 45 equals a b squared. And it says solve for a, so I'm going to divide by b squared. That gives me a equal to 45 over b squared. Step 2 says substitute the second point, which is 3, 135, and the previous solution, which is a equals to 45 over b squared, into my exponential function, which is y equals ab. So here, my y from my second point is 135, equals a from my previous solution, which is 45 over b squared, times b to the x, which I know is 3. Now I want to solve, so that gives me 135 equals my b squared cancels with b cubed, just leaves me 45b. Therefore, b is equal to 3. Now it says I also want to solve for a, and I can do that because I know that a is equal to 45 over b squared. A equals 45 over b squared. Well, b is 3. 3 squared is 9. So a is equal to 5. Now I just substitute a and b into my exponential function. Y equals abx. I have y equals a was determined to be 5. B I found to be 3 to the x. So a graph that goes through 2, 45 and 3, 135 has an exponential function of y equals 5, 3 to the x. And since b is greater than 1, this actually is going to be a growth exponential function. Similar example, I want to write an exponential function, y equals a b to the x, for a graph that includes the given points, which are 1, 2, 3, 32. The procedure is given to us. I want to use the first point and solve for a from my exponential function. So I have y, which I know to be 2 from my first point, equals a, b, and x is 1. I want to solve for a, so I'm going to divide by b on both sides. A equals 2 over b. Now I'm going to take the second point and my previous solution and substitute back into my exponential function. My second point, I know y is 32. A is known to be 2 over b. And I have b to the third power. And that's going to give me, when I simplify, 32. That b cancels 3 into 2, so that's b squared. I have 2b squared. So b squared is equal to 16. Therefore, b is equal to a plus or minus 4 when I take the square root of both sides. Now, I need to go back and solve for a. Well, I know that a is determined to be 2 over b. So a equals 2 over b. But I have two values for b. I have a positive 4 and a negative 4. But from my second slide on this section, it defines that b in an exponential function must be greater than 0. Therefore, I know that negative 4 will not be used. So I'm just going to use the positive 4. So when I substitute in, I get 2 over b, which is 4, equals 1/2. Now I finish up by substituting a and b into my exponential function. I have y equals a, which I determined to be 1/2, times b, which is a positive 4, to the x. So my exponential function is a growth of y equals 1/2 4 to the x. My last slide, I want to determine without graphing whether each function represents an exponential growth or an exponential decay. That is easy just by determining my value for b. On my first example, b is between 0 and 1. Therefore, this is a decay. My second example, my b is greater than 1. Therefore, this is a growth. My next function, y equals 3 times 7 to the negative x power, is really y equals 3. And since this is a negative exponent, that really can write this as 1/7 to the x. Now, b is really 1 over 7, which means it's between 0 and 1, so this is a decay. That only occurs if my exponent is originally a negative exponent of negative x. Next, I have a 2/5 for b, which means b falls between 0 and 1, and therefore this is also a decay.